The most important class of matrices in the context of eigenvalues and eigenvectors are in fact symmetric matrices. Symmetric matrices have very important properties when it comes to eigenvalues and eigenvectors that will also allow us to find or describe generalizations of the concepts of eigenvalues and eigenvectors and the diagonalization of a matrix, not just for square matrices, but also for rectangular matrices. There, the decomposition is called the singular value decomposition, and I'll introduce it, or to be able to introduce it, I have to first talk about symmetric matrices, and then we'll talk about the singular value decomposition of any rectangular matrix. So, just to remind ourselves that we're talking about symmetric matrices, instead of using the letter A, I will use S, and I will say Sx equals lambda x to hint to the fact that in this context, x is an eigenvector corresponding to the eigenvalue lambda. Now, there are many things about eigenvalues and eigenvectors that I am not completely describing in this class, and the reason for that is they require you to know complex numbers. That is not a prerequisite for this course, and I'm not going in that direction. It's just beyond the scope. But what is important to realize is that some matrices have complex eigenvalues. However, symmetric matrices always have only real eigenvalues. So one important property about symmetric matrices, so let me say properties here. And I won't prove them because these proofs will require that I use complex numbers. So we'll just remember and understand them and see how we can use them. So the first thing is that all eigenvalues are real numbers. So this is good news for us. It means we can work with these matrices. Second thing that is very important is that the eigenvectors can be chosen orthonormal to each other. Right, so orthonormal means they will be mutually orthogonal, and we can choose them to have length 1. Eigenvectors don't have to have length 1. If you have an eigenvector, any multiple of that eigenvector is also an eigenvector corresponding to the same eigenvalue. So it is up to us to choose their lengths to be 1. And if you realize here, orthonormal will hint to the eigenvector matrix being an orthogonal matrix, provided that we have enough of them. And the third property that is very important is that symmetric matrices can always be diagonalized. What that means is that they will always have enough eigenvectors that are linearly independent, or we could choose them to be orthonormal. In general, matrices don't have this guarantee that they can always be diagonalized. The condition for diagonalization of a matrix is that the matrix has enough eigenvectors. So for an n by n matrix, we will need n linearly independent eigenvectors to be able to diagonalize a matrix. And in the case of symmetric matrices, the important thing is that they will always have enough eigenvectors. Now, eigenvectors, this doesn't mean that all eigenvalues of a symmetric matrix are different. They can very well be repeated. The symmetric matrix could have just one eigenvalue. Such example could be the identity matrix, for example. The identity matrix has all eigenvalues equal to 1, and yet all vectors are eigenvectors of the identity matrix. And certainly the columns of the identity matrix are eigenvectors of the identity matrix. So there you have orthonormal, an orthonormal basis of eigenvectors. Similarly, you could take the zero matrix. All of its eigenvalues are 0. It is a symmetric matrix. And then again, all vectors, the zero matrix times any vector will give us 0 times that vector. So you see there are some special cases where these things work, where you don't have to have distinct eigenvalues. And the reason I mention this is that if you have two distinct eigenvalues, the eigenvectors that come from those eigenvalues are linearly independent for every matrix. But when you have a symmetric matrix, they're not just linearly independent, they're orthogonal to each other. So the key is that when eigenvectors correspond to distinct eigenvalues, they're guaranteed to be orthogonal. So then this choice for us to have all vectors to be orthogonal to each other and then normalized means that if you have a repeated eigenvalue, you might not have all eigenvectors, or you may find vectors that are not orthogonal, but you could orthogonalize those vectors. So you can always choose that they be orthogonal. All right, now I want to prove, so I'm not going to prove this part. The reason is it includes complex numbers. This part and this part are in some sense equivalent. So if you have 4, you have 2. And the sufficient number of eigenvectors, I'm not going to prove that either. That is beyond the scope of our class. But 4 is something that we can actually look at. So let's see why, when we have two eigenvalues, two distinct eigenvalues for a symmetric matrix and their corresponding eigenvectors, why is it that they have to be orthogonal to each other? So assume we have a symmetric matrix S with an eigenvector x giving us lambda x. And let's say we have another eigenvector y with eigenvalue mu, for example. That should be a y. Oops. So we are assuming that lambda and mu are different. And what we want to show is that, so these are our assumptions here, that x transpose y is 0. This is what we're trying to prove. Well, let's look at this x transpose y, or rather, let's look at how we can show this to be true. So I can say Sx, if I do this, Sx transpose y. What is this? Well, on the one hand, Sx is lambda x transpose y. Now, lambda is a number, so transpose doesn't really work on the number. So we just have lambda x transpose y. Okay? We don't know what x transpose y is. We're trying to figure it out. On the other hand here, I could first transpose the product s times x. I don't have to multiply the product. I can first transpose and get x transpose S transpose Y. Now, S is a symmetric matrix. What that means is that S transpose is the same as S. So in fact, here I have X transpose S, Y. Now, what is S times Y? Well, S times Y is simply mu times Y. So I have X transpose mu Y. Now, mu is a number, so I can flush it to the left. So I have mu times X transpose Y. So if you take a walk along this equality, what do we have? We have that lambda times X transpose Y is equal to mu times X transpose Y. If I bring everything to the same side, I have lambda minus mu times X transpose Y equals 0. Now, I have a product of two numbers. X transpose Y is a number. And the product of the two numbers is 0 if and only if one of those numbers is 0. So either lambda minus mu is 0 or X transpose Y is 0. But we assumed here that lambda is not the same as mu. That translates into lambda minus mu not being equal to 0. So then we see that X transpose Y must be 0. So this is not 0 by assumption. And so in conclusion, X transpose Y must be 0. And that means that the vector X is orthogonal to the vector Y. Okay, so this was proof of number 4 here, which actually implies number 2. I am not going to prove why we have enough eigenvectors, and I'm not going to prove why the eigenvalues are real numbers. Those are just facts that we are going to use, but we know that orthogonality of different eigenvalues, that orthogonality of eigenvectors that come from different eigenvalues is guaranteed for symmetric matrices. Now the question is, what do these properties give us? Well, if we can choose the eigenvectors to be orthonormal, then the eigenmatrix is going to be an orthogonal matrix. So for symmetric S, we can choose orthogonal eigenmatrices. So you see, because of that, what we get is that the diagonalization of a symmetric matrix looks like this: Q lambda. Now, so remember, we're using Q's for orthogonal matrices. So this is just a reminder. I'm moving from X to a Q. And the inverse of an orthogonal matrix is simply its transpose. So in the case of symmetric matrices, we actually have, we can get away without finding any inverses of matrices, right? We have this right away. The inverse of the symmetric matrix, we get the diagonalization of S inverse immediately as well. But I guess that is not so interesting. We've already seen that. Now, from here, we get a very, very important result, which is actually also referred to as the spectral theorem. And what it says is that when you have a symmetric matrix, you can represent that matrix as a sum of rank 1 matrices as follows. You can write it as lambda 1 Q1 Q1 transpose. So remember, this is a rank 1 matrix, plus lambda 2 Q2 Q2 transpose, plus lambda n Qn Qn transpose. Now, a reminder, the lambdas don't have to be distinct numbers. The point is that these vectors Q1, Q2, Qn, they are eigenvectors of S corresponding to eigenvalues lambda 1, lambda 2, lambda n, and they're orthonormal. So this formula over here, this factorization that we have here, is equivalent to this sum. So you can split S into a sum of rank 1 matrices along different eigendirections, if you like. How to see that this is so, that these two things are equivalent? Well, matrix multiplication takes us there. We'll take a moment. I want to show you how this works, why that's the case. So if I have S equals Q lambda Q transpose, we can represent the matrix Q through its columns, Q1, Q2, Qn. These are the eigenvectors of S that are chosen to be orthonormal just because we can, corresponding to eigenvalues lambda 1, lambda 2, all the way to lambda n. And then in Q transpose, I have these same vectors, but now as rows. Q1 transpose here, Q2 transpose as a second row, and Qn transpose as the last row. Now, let's say I carry out this multiplication first. It doesn't matter. It doesn't have to be this way. I could carry out lambda times Q transpose first. Either way works. So I have equals. So what does this multiplication do? Well, I'd rather look at the action of this matrix onto this matrix than the other way around. How do you get, when lambda works on the right-hand side of Q, it acts on the columns. So then you ask yourself, how do I get lambda from the identity matrix? By acting on the columns of the identity matrix. Well, you multiply the first column by lambda 1, the second column by lambda 2, the last column by lambda n. So the product of the first two matrices is simply lambda 1 Q1, lambda 2 Q2, all the way to lambda n Qn. And then the Q transpose matrix is what it is. It's the same thing. And now we carry out the column by row multiplication way of multiplying matrices, and we end up with lambda 1 Q1 transpose plus lambda 2 Q2 transpose all the way to lambda n Qn transpose. Okay, that was the claim. I will write a little note here that this is a decomposition of S is a sum of n rank 1 matrices. Now we will see when we talk about the singular value decomposition, it will be something very similar to this, where all the lambdas, they won't be called lambdas there, they'll be called sigmas. They will all be positive numbers, and I will talk about how that is useful in applications. Now, all that's left is for us to see an example on how to work with symmetric matrices and how to choose eigenvectors to be orthogonal. So let's see. Let me find an example. Okay. Let's look at this matrix. We have S equals 1, 0, 2, 0, negative 1, negative 2, 2, negative 2, 0. And what I want is to find an orthogonal matrix Q that diagonalizes the symmetric matrix. And lambda 2, obviously. So find Q and lambda such that S equals Q lambda Q transpose. Okay, first things first. I mean, there is nothing new here. We have to find the eigenvalues and the eigenvectors. So we start with S minus lambda I, and we want to find that determinant. So we have 1 minus lambda, 0, 2, 0, negative 1 minus lambda, negative 2, 2, negative 2 minus lambda. All right, now let's see how we can solve this. Is there any way that will make things a little bit easier? Well, I'm not seeing anything obvious, so I will just continue with expansion maybe along the first row. I don't really want to use the formula, so I'll do expansion along the first row. So I have 1 minus lambda. Remember, expansion along the first row would be plus, minus, plus, but the minus corresponds to 0, so I'm just going to ignore it. So I have 1 minus lambda times this smaller determinant of negative 1 minus lambda, negative 2, negative 2 minus lambda. And then plus 2 times 0, negative 1 minus lambda, 2, negative 2, equals. So this right-hand matrix is already, we already see what the determinant is. Here the determinant is 2 times 1 plus lambda. Whereas this side would be the minuses in minus 1 minus lambda and negative lambda cancel out. So really you have lambda times 1 plus lambda and then minus 4. Okay, so the determinant is 1 minus lambda times lambda 1 plus lambda minus 4 plus 4 times 1 plus lambda. And I'm not sure how much I can factor here. Perhaps not very much at all. Okay. I feel like this should have been easier. Maybe I'm not seeing something. 0. Maybe not. Okay. So let's expand. I have here 1 minus lambda. I feel like I should be able to do this easier. Let me write this for a moment. Bear with me. I have not solved the problem before, as you might be able to tell. So then I have minus 4 times 1 minus lambda plus 4 times 1 plus lambda. I wonder if things cancel out here. The 4's will definitely cancel, so that's nice. Okay, so here, this part is negative 4 plus 4 lambda plus 4 plus 4 lambda. So you see these two cancel out and I have lambda. I don't want to expand the left-hand side because lambda is a common factor. So actually I have here lambda. So this part is 8 lambda, okay? And lambda now is a common multiple from here and from here. So I'll factor it out and then I will have 1 minus lambda times 1 plus lambda plus 8. Okay, so that equals lambda times 1 minus lambda squared plus 8, which is lambda times 9 minus lambda squared. And that is equal to, I'll continue on a new page. So finally, s minus lambda I equals, so this is what we had on the other side without that. 9 minus lambda squared factors into 3 minus lambda and 3 plus lambda. So the three eigenvalues are lambda 1 equal to 0, lambda 2 equal to 3, and lambda 3 equal to negative 3. So since all the eigenvalues are distinct, I know that I'm guaranteed to have orthogonal eigenvectors. I don't have to worry about orthogonalization in between the eigenvectors. So I do need my matrix S. I need to now work with S. To find the eigenvalue, or the eigenvector corresponding to the zero eigenvalue, so that says that this matrix is singular. I was not able to see that immediately, although now I am. Yeah, I should have been able to see that. And then it still wouldn't have been enough, but, or maybe it would have. It would have told me that the other two eigenvalues need to add up to 0. Okay, so if you pay attention, if you add these two rows, what you will get is 1, negative 1, 0. So you could carry out elimination. Perhaps I will, just to remind you of how that works. But really, if we do column 1 plus column 2, we're going to get a half of column 3. So if I multiply that by a negative 2 and add column 3, I'm going to get 0. So I immediately know that the eigenvector corresponding to this S is x1 equal to negative 2, negative 2, 1. I just know that this vector works by observation. You can quickly check to make sure that S is orthogonal to this vector. So this is the null space. We're looking for the null space of S. And if it is, it is orthogonal. So you know that it works. If it's orthogonal, it works. Now, we're not looking for x1. We need to have normal vectors, so we need to have their lengths equal to 1. The length of x1 is just 4 plus 4 plus 1. That is the square of the length. My apologies. So that's 9. So the length of x1 is 3. Therefore, the first vector in the matrix Q is 1 over 3 times x1. So I have to normalize the vector, otherwise I'm not going to find an orthogonal matrix. Okay, now that I have found this, and again, you can find x1 by observation in this problem, but also you can start with elimination. So I will repeat a process that I've shown before. Bear with me. So to find x1 via elimination, we'll carry out elimination on the matrix S. Again, this whole discussion corresponds to the eigenvalue lambda 1 equal to 0. So we'll eliminate with the first pivot. The operation will be R3 minus 2R1 into R3. We will get 1, 0, 2, 0, negative 1, negative 2, then 0, negative 2, and then negative 4. So now you see that the next step of elimination will simply get rid of the last row. And we could also multiply the second row by a negative 1 to get the two pivots to both be equal to 1. I guess I could have done the following. I could have said here R2 minus R2 into R2, because R2 is not involved in that first operation, and then I would have pluses here, so I don't have to do that in the next step. And then elimination R3 minus 2R2 into R3 would give, I guess, plus here because I flipped the signs. It would give us 1, 0, 2, 0, 1, 2, 0, 0, 0. So this is the reduced row echelon form of the matrix S. The first two columns are pivot columns, and then x3, or the third variable, is a free column. So this one is the free variable. And to find the special solution to this problem, we set the third component. So here's special solution. Special solution to Sx equals 0, right? We're trying to find the null space. So the special solution will have 1 for the free variable, and then you're trying to make sure that the two rows comply or solve the problem Sx equals 0. So if you look at the second row, that means 1 times the second variable plus 2 times the third variable should be 0. So since this variable is 1, you have really x2 plus 2 is 0, so x2 better be negative 2. So that's how you find negative 2 here. And then the similar logic gives you a negative 2 in the first position. So that is the vector x1 that we found. Those of you who can see x1 right away, even if you have, say, 2, 2, negative 1, or if you have a half, a 2, well, a half, a 2, that wouldn't make much sense. So you're likely by observation to either have negative 2, 1, or to have 2, 2, negative 1. You could also, I guess, have 1, 1, negative half, or negative 1, a half. So any multiple of that vector will do. If you can get it by observation, by all means do it by observation. If observation doesn't help, then carry out the elimination step. Okay, so we've taken care of lambda 1. We have found the corresponding eigenvector Q1. Now we need to do the same thing for lambda 2 equal to 3. I will need the matrix again. So here's my matrix, and I want to work with lambda 2 equal to 3. So what we now need to do is, so our lambda 2 is now 3, so we have to find the null space of S minus 3 times the identity. That's the next step. That's where the eigenvector for lambda 2 is going to be. So S minus 3i equals, remember, we're subtracting a 3 along the diagonal. So we have negative 2, 0, 2, 0, and then negative 4, negative 2, then 2, minus 2, negative 3. It's not very obvious that this matrix is indeed diagonal, but we can simply, sorry, diagonal, I meant to say singular, but it does have a 0 eigenvector. We can just carry out elimination. We don't have to be able to see everything by observation. So if I eliminate here, I will get, I should do R3 plus R2 plus R1, sorry, into R3. And I will get negative 2, 0, 2, 0, negative 4, negative 2, and then 0, negative 2, negative 1. And now you see that the third row is a half of the second row. So if we carry out that elimination step, so we have R3 minus a half of R2 into R3. the minus comes from the fact that their signs are the same. We're going to get negative 2, 0, 2, 0, negative 4, negative 2, 0, 0, 0. And to get the reduced row echelon form of the matrix, we should do negative 1/2 R1 into R1, essentially divide by the pivots. And then negative 1/4 R2 into R2. And the resulting reduced row echelon form will be simply 1, 0, minus 1, 0, 1, positive half, 1/2 here. And then everything else is 0. Now again, the pivot columns are the first and the second one, and the third column is free. So the special solution here, which I'm going to call x2 as a vector and not as a component, will be 1 for the free term. And then then I have 1, or the second component x2 plus 1/2 should be 0. Then the second component should be negative 1/2. You can just test to make sure that you see, it doesn't matter what the first component is. This vector is orthogonal to the second row, so we know we're on the right track. And then we want to make this vector orthogonal to the first row. Well, now this 1/2 doesn't play a role. As long as the first and the last component are the same, the first row will be orthogonal to x2. So again, to double check our solution, just make sure that this reduced row echelon form matrix times the vector x2 gives you 0, and indeed it does. This vector is not of length 1, so what is the length of the vector? Working with the square is easier, so then I have 1 squared plus 1/2 squared. I don't have to worry about the minus because I'm squaring everything. Plus 1 squared, so that's 2 plus 1/4. When I add those up, I get 9/4, and therefore, which is 3/2 squared. Now you see that the norm of x2 is just 3/2. Therefore, the vector q2 will have to be 1/3/2, but 1/3/2 is 2/3 times the vector that we found here. 1, negative 1/2, 1. Of course, we could also factor out the 1/2 if we don't like to have the 1/2 inside. So if I factor out 1/2, what I will get is 1/3 of 2, negative 1, 2. So that works as well. We don't have to work with the special solution that is in the null space. And finally, so now we have the second vector over here. And now we have to find the third vector. I'll copy that one more time. I do admit finding singular eigenvectors does take a bit of time because you're solving for a null space 3 times. Now, lambda 3 here is minus 3, therefore we need to look for the null space of S plus 3 times the identity. So S plus 3i, now I'm adding a 3 along the diagonal. I will have 4, 0, 2, 0, 3, negative 2, 2, negative 2. Oh, sorry, that should not be a 3, that should be a 2 over here. The 3 is in the third row. Now we need to carry out elimination. So the elimination step I would have to be working with halves. If I don't want to work with halves, I can divide the first row by 2 first. So I could just say, and I will do the same with the second row as well. So I will say 1/2 row 1 into row 1. And I will say 1/2 row 2 into row 2. This is allowed, even though this is not our typical approach, but the number is just sort of give us a hint that this is not a bad thing to do, to avoid thinking in fractions. Now I will eliminate. I have R3 minus R1 into R3. What I get is 2, 0, 1, 0, 1, negative 1, 0, negative 2, and a 2. Now I see that the next elimination step is going to produce zeros in the third row. I'm not going to write that, so I'm just going to say ignore the third row. These are the two pivots. This is not the reduced row echelon form of the matrix because the first pivot is not 1, but that's okay. We don't always have to get to the reduced row echelon form. This will be the free column. So I will find x3, the vector x3, by setting the free column equal to 1. And then I need to figure out what the other two need to be. So this second row says 1 times the second variable minus 1 should be 0. So then the second variable better be 1. So you see here, if you multiply the second row times this vector, it doesn't matter what this is because there is a 0 in the second row, you get 0. So this times this gives you 0. That's all you want. And now you want this vector times this vector to be 0. Now this one doesn't play a role. The first row over here has a 0, so it doesn't matter. So you want 2 times this vector plus 1 times that. So you want 2 times this component plus 1 times that component to give you 0, so that this component needs to be negative 1/2. If you don't want to have the 1/2 inside, you could choose another x2. You could just multiply this vector by 2 and have, another x3. Your x3 could very well be chosen to be negative 1, 2, 2. That's another good choice for x3. And I suspect most of you will like it. The only issue is that this first approach is how we talked about standard solutions when we look for a null space. This is you being able to understand that I can take any multiple of the eigenvector, that 2 is an eigenvector, and I don't have to work with fractions. So let's say we first find this, but then we adjust and we say, okay, this is x3, and I'm just going to cross that off. Both are correct, but work with the second one. So then what is the length of x3? Now I'm going to bring everything here. So the length of x3 squared is this negative 1 squared plus 2 squared plus 2 squared, which is 9, which is 3 squared. So the length of x3 is 3. Therefore, q3 equals 1/3 of this vector, negative 1, 2, 2. Now note that there are only 2 choices for q3. Could be this q3 or could be minus this q3. So we always do have 2 choices for the vectors q, but that's it. We don't have more than 2 choices. Whereas for an eigenvector, you have infinitely many choices because you can multiply that vector by any number and get another eigenvector corresponding to the same eigenvalue, as long as you avoid multiplying by 0. All right, well, now we found our q1, q2, q3, and the matrix lambda. So finally, we just have to put all of it together. So S equals, I actually do need to look at the q's. So the first q is 1/3 of negative 2, negative 2, 1. And interestingly, they all have 1/3, right? So I can put 1/3 here, negative 2, negative 2, 1. Then 2, negative 1, 2. And I feel I'm going to want to change some things. And then negative 1, 2, 2. This would be the matrix Q. Now I could actually choose my matrix Q symmetric. How could I do that? Well, note that if I have plus here and plus there and minus there, I will have a symmetric matrix. And I can very well make that choice because, as I said, all of the Q's can have can be multiplied by a -1 and give us another eigenvector. So here in this Q1, I could very well make this choice if I want. And I do like symmetry, so let's make that choice. It's not necessary, but it can be done. I can take Q1 to be minus this special solution of x1. I'll have 2, 2, -1 there. Of course, I could also have chosen Q3 to be minus what it was, but either way works. So for that new choice of the Q's, I will have 2, 2, and a -1. And I actually have a symmetric Q matrix. This doesn't always happen, but in this particular case, it did. Then the matrix lambda comes. So we did 0, 3, -3. The first column corresponds to eigenvalue 0, the second to eigenvalue 3, and the third to eigenvalue -3. And then Q transpose, so this is lambda. And Q transpose is, again, 1/3. And in fact, because this Q is symmetric, you have Q again. So we have 2, 2, -1, 2, -1, 2, -1, 2, 2. Whether we've transposed it or not, the result is the same. So for this particular S, we found Q lambda Q to be the diagonalization. This is particularly neat. So we found a symmetric orthogonal matrix. Okay, that is more than enough for symmetric matrices.